Yo, yo. I think I found my ideal memory management strategy. It's feeling pretty good, feeling pretty good. Over the past little bit, I've been writing a lot of Zig, right? People who've been watching the channel will know that we've been in the Zig land a lot, right? And one of the things that makes Zig nice is that there's no complexity that's added on from doing things like RAII, right? You manually manage your memory, but they provide you utilities to do so in a way that isn't like too painful, right? So your typical workflow would be like let's say it's file typical Zig. You do like pub function main, right? In here you go like I'm gonna alloc a thing, so like some like int pointer is gonna be like alloc dot create i32, right? This is like your typical Zig thing, right? And then you go in here and you go like, okay, well at some point I'm gonna have to free this memory, so I'm gonna like use X in some way, right? I'm gonna do some stuff to it, and then eventually I'm gonna free it. So you'd go like alloc destroy X, right? This is your typical C style allocation free, right? That's cool. But it would be nice if you didn't have to like get all of these right all the time. You don't have to use like go-tos the way you would in C. In Zig, they give you this little defer keyword. So all you do is you say defer this thing, and this runs at the end of the block, which is great for this scenario, right? That's wonderful. Where it starts to get a little bit hairy, and into a bit of a realm that I'm not really too happy with, is if you're going to do something like, you're going to do like make X, right? And he's going to return, some i32 pointer, and he's going to take in his allocator like this, allocator, yeah. So we're going to do the same thing, right? But we don't want to do this anymore, right? Because we're giving it back. So we return X. Let's say that we're still going to increment him, and really, in reality, we should actually initialize it to some value as well, right? So we'll do something like this. Now, what if, as part of this thing, we want to, I don't know, allocate some other thing and use it? We're going to pretend that you're going to try to allocate Y as well, right? Defer alloc destroy Y. Now, in this scenario, all of a sudden this thing can fail. So if this fails because this allocation failed, then this X will leak. So what we have to do here is to go like error defer alloc destroy X, which says like, hey, if you bail out for any reason other than like the expected case where we're returning X, then like let's get that thing out of there, right? Chill. But this can be like a little bit error prone. I've like come across this many times where like I copy paste to block, I change the variable name, and then I forget to change this. Now all of a sudden, if this fails, this will destroy X, and then we'll try to destroy X again, double free, bing bang boom, program crashes, blam, that sucks, right? And so it's been bothering me that like we are seeing this like unrun code that could like have catastrophic effects on our application, right? If we do like a coverage report of our image editor, we can like take a look at this and see like, okay, here when we initialize our renderer, look at all of these chunks of code that we've probably never run, like ever, right? And it's just like, yeah, it's not great. So the thought here is, can we fix this? And I think the answer is yes, right? We can just take a different approach and just delete all of these error defers. I mean, that approach is, instead of doing this, what if we just deleted them, right? No more error defers, right? Or defers, like no more freeing of individual elements at all. Well, okay. Well, how would you manage that? Well, I guess you could just say that you have some sort of like pool of memory. Sorry, I shouldn't say no errors at all. We're going to say unconditionally, we don't need Y at the end of this, and we don't need Z at the end of this, right? Unconditionally, we don't need these. What we can do now is we don't have to worry about like an error defer here. We can say, make me a pool. Alloc pool is some sort of thing, right? And we'll say like make X, and we'll use like an allocator from a pool, like this. And all we'll do is we'll say, you know what, at the end of our application, we're going to deint the whole pool. Fuck it, right? And now, whether or not this succeeds or fails, now we don't have like a different case. Whether or not this fails, we're still going to deint the pool. Whether or not this succeeds or fails, we're not going to do anything with X. We're not worrying about it because we don't have to free individual chunks of memory. Here we could even choose, if we wanted, to not free these guys manually as well, that's kind of like going a little bit farther down the line, and we could say like, well, we know that in this case our pool is going to take care of that thing, right? If everything in here is temporary, we don't even have to care about any of these things if we know that. And so we've been kind of trending towards this a little bit, and this is like a strategy that I've seen online before. I've seen people talk about like arenas. Arenas are like, in fact, there are arenas in the Zig standard library. Even if we look up like Zig standard lib, and we go in here, we can look for arena allocator, and they have one of these guys, right? And the idea behind them is you allocate like some block of memory, or some block of memory gets like allocated for you. And as you allocate, you have like some pointer into the arena, and this pointer kind of moves up over time, right? That's great. So what you can do is you can kind of do this strategy where you create your like arena, and at the end of your shit, you like reset the arena. And when you reset the arena, this pointer just moves back here. And all allocations just move forward. You never free anything. You just reset the arena. That's pretty cool. That works. That does what I want. Now where that starts to fall over for us is we have kind of like many objects with different lifetimes, right? So in our image editor that we've been working on, we have like, maybe we show it. We have like images, right? This is like just a list of things, and we can like add or remove images, right? So maybe we want to create some sort of circle. We're gonna make like a little red circle, and then maybe we want to like draw a little face on him. So we're gonna like create a new drawing, and the drawing we're gonna like put some like let's maybe pick a color that doesn't suck so much, and then make it brighter, right? You're gonna maybe want to draw a little face on this guy, right? And then maybe we want to like make a composition of some of the other objects that we have, and we want to take like our picture of Cersei Lannister and our picture of our little face, and we want to like slam that on top, right? Each action that we take here creates a new object. And then maybe we decide, hey, there's like other stuff in here, we don't need it. So we'll delete this image, we'll delete this image, we'll delete this image. And now like, you know what, I don't really want this composition anymore, I'll delete that, right? All of these things, like all of these individual images or objects, they had allocations, right? And so if we were to just make one big arena and say, we'll reset it when we're done, we are kind of leaking memory for all of those things that we just created. And so, what's like the next approach that you would think of? Well, what if we just made an arena for each thing? Cool. So we're gonna say like, we could say like we have, object is a structure, and in here he has like an arena, which is a stud, keep arena allocator, right? And then we just like, allocate our stuff with this thing. Now, the problem here is that if we have many arenas, we still have to worry about freeing each individual arena directly, because what's happening when they make these allocations, they need to get the memory from somewhere, right? And so there's like Linux over here, right? The little kernel, and we talk to this thing and we say, could you mmap some memory, please? Please, just give me some memory. And the arena will like ask Linux to do this. Well, the hand wavy in Zig, the arena can use like a any backing allocator, but he's gonna ask someone for some memory every once in a while, and that means that like we need to return this memory back to the system when we're done with this specific arena, which is like, yeah, we do have to do that, but it would be nice if like, how do we say this? If we kept that property where we were saying before. Do we have our example still somewhere? We lost it, I think. But it would be nice if we kept the property that in the happy path, we still had this pool was like a sub pool of our global pool, right? What I'm kind of imagining would be pleasant is we have like an application pool, and in the application pool we have like object storage, object store, right? And in here we have like each individual object has like its own allocator. And as we add or remove objects to this thing, we can like delete their pools and get all the memory freed, while keeping like the nice behavior of when we free this pool at the very top, everything below gets freed as well, right? So if we have like individual allocators that all kind of like request memory from the system individually, we still need to free each one. So that's constraint one, is that we wanted a tree of stuff. Now the other thing that we have to think about here is an arena allocator is not very friendly to something like your typical growable array type. right? So in Zig, this is called like array list, right? And like the way that these things typically work is that you have some sort of like append function or push or something, right? And you say like, I'm gonna make some stuff and I'm gonna like put some numbers in here. And as I put some numbers in here, this thing, like we don't really know how big it's gonna be up front. So it's gonna start at like, maybe it'll start like 4 elements big. And when we get over 4 elements big, it goes like, uh-oh, we need 8 elements now. We're gonna double the size and we'll copy paste the existing 4 and then we'll start adding stuff more to here. Then you get bigger than 8 and you go like, oh, let's double in size again. And what happens here with like arenas is that every time you do this, you're basically wasting this memory, right? Because you can't reclaim it unless you reset the entire pool. And you could say, well, why don't you just like not use array lists? You could use something a little bit more intelligent, like something like chunks of arrays where every time you run out, you allocate a new one and then you link them together, which is like a good strategy. And that is the thing that we're doing partially. But if we're trying to like retrofit a new memory allocation scheme into like an existing application, that's a pain in the ass. And I don't want to do that, right? And so what we ended up doing instead is we ended up creating something that kind of fulfills all of these constraints. We made this thing, we called it Spheriphoria's allocator, Sphalloc, which sounds a little bit like phallic, which isn't really that great, but we'll live. And what this guy has is he has, well, we can actually open him up right now. Const Sphalloc. He has a block allocator, which is essentially like the thing that we were talking about before that says like, could I mmap some stuff from the system, please? Could I just get like system memory? And he has a list of children, as well as a general purpose allocator and a bump allocator. So the way this thing works is at each level, we have like block alloc, and from this block allocator, we do like a normal allocator, general purpose allocator. This thing supports like typical allocates and frees, and then we have our arena. Now, where this is getting a little tricky is usually when you're using like a general purpose allocator like this, you would still want to do like manual frees and stuff, right? But we don't have to do that. We don't have to do that because in the block allocator, we track every single page that's been mapped by the system, right? So what'll happen is the general purpose allocator, you'll say like GPA alloc some memory. Like you'll say like, alloc, some 4 ints or something, right? What he's going to do is he's going to be like, do I have any blocks of memory that will fit those 4 ints? And he might say yes, he might say no. And if he says no, then he goes to the system and he asks, or I guess in our case, he goes to the block allocator and he says, could I get like, 1 page of memory? Give me like a big chunk of it, right? Give me a big chunk of RAM. And then he splits up this RAM as needed. As you allocate and free stuff, he keeps track of like which chunk of big memory that it came from, and like he does stuff like double free protection and all that, right? Then as you use your array list with this guy, you can reuse segments of memory that you had freed before, which is a big improvement. Where we started to see problems with this, then since the block allocator is tracking all of your allocated pages, you never actually at the end of your application's lifecycle, at the end of all time, you don't have to call free on each individual thing that you allocated with this general purpose allocator. You don't have to do that anymore because we know which pages we blocked. So we just kind of like drop both of these guys. They're not important anymore, and we do like walk the list of blocks that we took and free each of those. Which gives us kind of like the properties of the arena allocator where we can like reset it and free all memory at once without having to lose the ability to do like individual allocations and frees. The downside here is that when we start like making different allocators for different things, right? We have like an object pool for like an individual image, right? We have like shader 1 and shader 2. Each of these guys has their own individual block allocator, general purpose allocator, and arena, which maybe come from some parent, right? So these are going to come from like all shaders, right? In all shaders, if we free all shaders, we free all memory from both of these guys, or if we free an individual one of these, we only free these guys, and we can keep going on. The problem here when we got to this point is that pages pulled from the system, they're too big. too big. 4096, it means that if we're making like tons and tons of objects, we're spawning these allocators all left, right, and center, we run out of RAM. Right. Well, we don't like run out of RAM is strong, but each like small thing now. Say we were like spawning something, and it's like caching like his like name, and like maybe like a few, maybe he's storing like maybe like 500 bytes of data, right? And so we heap allocate him because it makes sense, so that he can have like same storage size as everyone else, whatever, yada yada. Yeah. So if we do this, then the minimum amount of memory we can use is 4096, and likely if we're kind of splitting use between the arena allocator and the general purpose allocator, which we might, then we're kind of looking at like minimum 4096, probably 8192 bytes, right? Which means that we have like, what is this, like 1/8, half of 1/8, so like 6% utilization of the memory that we allocated. Ugh, gross. And often it's actually worse than this. So the next thing that we tacked on here was we added a piece that sits between the page allocator and our thing. So we added this thing, we call it tiny page alloc. And basically this guy's job is to take chunks of 4096 or greater, right? And he wants to split them up into blocks that he can hand out. So he's going to split this up into really like, a bunch of 256 byte blocks, right? Then all of a sudden, this guy over here, the block allocator that's taking pages for our general purpose and arena allocators, he now knows, oh, I only have to take 256 bytes. Which means that the overhead from this drops from, 8192 over allocated for 500 to like 0, because like maybe like we're talking like maybe like 10s or 20s of bytes overhead, because like we can now allocate at this granularity. And so that's the scheme we ended up with. We have at the root we have tiny page alloc. Tiny page, geez, you guys can read that. We'll remember. This guy is used in a spherophoria allocator who has a block allocator. Block allocator talks directly to tiny page allocator. He gets pages from the system now in like 256 plus byte chunks. Then from here we have like an arena and a general purpose allocator that talk to the block allocator. And so the block allocator remembers what these guys have allocated. Boom, we can clear out these pools. All that works wonderfully. Is that it? I think no. I think there's something else we have to talk about. But I don't remember. I lost my train of thought. Yeah, so pretty happy with that. Where this like really shines in our application is we can kind of show like how this change in memory management like affects large portions of our thing. So first of all, we had our initial problem. Our initial problem is that we hate how many like error defers, untested error defers there are, right? So we can kind of like grep our diff here for how many error defers that we've managed to remove and how many we've managed to add. So we've managed to remove 175 error defers. We've added 11, and how many are left total? I haven't actually checked that. 192. So we removed like about half of them. There's still quite a few. Oh, no, sorry, this is the diff. We want to grep. Sorry. We want to grep error defer in source. And we probably want to do, recursive grep. And get ls files, maybe, source. And then xargs grep error defer. Yeah, so we moved 175 error defers, and there's 24 left. That's a huge improvement. So like the mental complexity of having to like be like, oh, I'm gonna make this thing, but don't remember to free it if something else goes wrong later. That's like almost completely fucking gone. And we can see some like pretty huge improvements in that area if we look at like the diff here. So if we look at like our GUI framework that we've written as part of our image editor, And we look at maybe something like the combo box, I think is a good example of this. Yeah. Okay. So combo box. What are we talking about here? In some cases, we have like lists of things. So maybe we are trying to draw on top of something. We make a drawing, right? And we want to draw on top of this picture that we had, but maybe we want to change the picture, right? So we want to do, pick what picture we're drawing on top of. This here is what I'm talking about, this combo box. So what happens is when I click this button in the GUI framework, he spawns this list of stuff. And the list of stuff is like dynamic, and also this widget doesn't always exist, right? So somebody before would have been like, okay, I need to allocate all of these widgets, I need to put them in this list, and when we're done, I need to make sure that I like free kind of like the whole tree of things. And what really sucks is since this is like a tree of widgets of some form, there's kind of like, I think it's something along the lines of there's like individual text elements. There's kind of like an array of text elements that are sitting in a probably box. Actually, we can just look. Let's just look. So let's look at the before here. So as we create this thing, we create a stack of elements, which says like, let me put like two things on top of each other. Then let me create a frame out of that thing, where the frame is, I think, the frame says, I'm actually, what the fuck is a frame? I need to refresh my memory. This guy's job. I see. It's like at a border. It's at a border. So if we look at this thing and we go back to this, it's the frame is the part that frames this thing, right? So there's kind of like this inner section here and then this outer section here. The frame is the outer section. So if we look at, what was it? It was a combo box. And we look at the before here. We have a stack, so like the background plus the stuff on top. Then we have a frame. In the frame, we have our selectable list, and we then put the selectable list in the frame. Then the whole frame goes into scroll view, and then the whole scroll view goes in a box, right? And the box is there to kind of say, like, we're going to make sure that the scroll view doesn't fill the whole screen, but does like fills this like one particular area. And if you look at like the memory management that we have to do to make this work, it's like, first we try to allocate our stack, and we go, okay, well maybe like the stack will fail later. Then we say like, okay, let's allocate this rectangle for like the background, and then we call this thing push or dinit widget, and we try this thing. We say like, okay, we're gonna give the rect to the stack, and I guess like after we put the rectangle in the stack owns the rectangle, which gets a little confusing. So we have to say push or dinit so that if this thing fails, it frees the rectangle, or else when we call this error defer up here, then it will like double free the rectangle. No good, that's bad. Then there's some stuff that doesn't really fit as well into that paradigm. So we have like this list of stuff, and we have the same problem where we're like, okay, so if we fail to do something, then we're going to free the list, and we try to put the list in the frame. Now the frame owns the list, and it's like, okay, so then we have to break out of this block, because now that the frame owns the list, we wouldn't want to double unit the list anymore. So this error defer for the list, that can't happen anymore, because like, if the frame units later, that's a problem, right? So then we go over here and we try to make a scroll view for the thing. We put the frame, we say, frame. If we fail to add the frame to the scroll view, then we should denit the frame, but only until we have the scroll view. Then we should do the same thing here. We were creating like all of these scopes and managing each of these individual pieces really independently, and that sucks. So with the new scheme where we just say, fuck it, these guys can all leak and our pools will take care of it. It's just so simple now. We make the list, we make the frame, we make the scroll view, and we put them in the box. And it's like, that's it. There's no more of this like trying to manage who owns what and for what, at what point does who own what. It's just like all of that is just gone, and it's sick. And if we look through like kind of like the whole change set for this stuff, we've actually managed to completely remove the concept of like deinitializing our widgets. Our widgets all just leak. We don't have to like walk this widget tree and figure out who owns what and keep track of all of that and like free each of our individual components. It's just gone. It's all just gone, which is like hype. In fact, I bet we could maybe do that same grep thing, and we could look for maybe, how many times did we remove a function called dinit? How many times did we do that? So let's just make sure that this looks about right. Yeah, so we've managed to remove across our application 64 dnits, and how many are left? So maybe we want to do grep function dnit. There's 11 left. We've moved a good chunk of them. There's like, we don't have to do cleanup anymore, which is huge for us. Yeah. So pretty happy with that. There is like some trade-offs here for sure. This did simplify a lot of like this type of work that we were talking about in the combo box, right? This feels like so much better, like unfathomably better, right? But a few things that are not as good is the old way of doing things that I was doing before. You have one allocator at the root, one general purpose allocator, and use that for everything. One, it was simple. Anytime you had to allocate anything, you're just like, I'll use the one allocator. Now you have to be very careful about knowing the like where things live, which means that there were a bunch of APIs that I used to have that were like, I used to do like, I have some structure, right? And this structure might have an array list in him. Unmanaged. So set file type equals zig. You know, we might have stuff like we have some integers in here, right? Values. And in here, I would have like a function that's like, you know, push value, and the value, we would just take in an allocator here. And we would know that like, how do you do this? Self is a x. And then you do, you know, void, whatever. Then you would know, you just go like, oh, self values, I need to use this allocator, and I push, you know, something in it, right? This is like a lot sketchier now because you need to remember which allocator you're using for exit every time. So I'm moving a lot more towards like storing allocators inline like this and then not passing them in. And like the new pattern is just like we only pass in allocators if we're like getting a thing out. If we're getting a thing out, we get it out on this allocator, but like you own your own storage and you just like initialize with whatever allocate. You just use whatever allocator you were initialized with and just don't forget. The other thing that kind of sucks is now that we're like intentionally leaking, we don't get like the benefit of letting Zig's allocators tell us if we have forgot to free something. So before you would have something like you'd be in main, and in here you're like, I have some general purpose allocator, right? And you would say like, at the end of the application, can you like dnit this thing? And what this would do is it would actually like start like yelling at you if there was anything that you ever allocated from this thing that was not freed. Now we're kind of not freeing by design, which means like it's easier to introduce like a memory leak, right? But it's easier in some ways. In the way that like your pool will always be deinted, like you don't have to worry about that. But if you were to like maybe just keep allocating from some long-lived pool and you just forgot that you were doing that and you just like drop the objects like you normally would, there's a chance of leaks. So my fix for that is that I added this like debug view that kind of graphs the memory usage of different like subsystems over time. So every time we make like a new allocator, we give it a name and we can like look at the memory usage of that thing here, right? So we can see that over time, memory tracker snapshot is going up in RAM because we have like more samples that we're like trying to remember, right? We can do things like we can create a new drawing, and as I start like, you know, really like wiggling the mouse over here, we can see that like the drawing object here, drawing object memory starts going up, and as a result, you know, all of object storage memory usage goes up, right? But we should also be able to see that when we delete this object, you know, drawing object memory goes back down to 0 and the object storage goes back to where it was. And so like, you know, this has been like a pretty, I think this like combats the like leakies problem to some extent. I was seeing before that like if I spam added lots of objects and then deleted them a few times, so I'm just like, you know, delete, spam, delete. You know, here we're now seeing that like object storage like goes up and down, but it kind of like flattens back out to where it used to be. You know, there were cases before where I was like, I messed up a couple times and I was seeing like allocations increase over time. But I think that's compatible, and I think that that's like mostly a familiarity problem. We'll see where it goes. Anyways, yeah. I'm pretty happy with it. Pretty happy with it. Code for this, if you want to take a look at the allocator implementations, they'll be on GitHub under the svimp repo for image editor, Spheriforia's GIMP. And in here, there's like this like allocator section somewhere. Probably not on master. It will be on master. Right now it's under the branch called error removal, but you know, all the codes here if you want to take a look at it. Something that I didn't really touch on is that we were talking at some point about how, I guess we lost it. We were talking at some point about how big pages were too big, right? So we made this like tiny page, right? Now, when we make this like tiny page allocator and we try to like use it with a general purpose allocator or a block allocator or bump allocator, arena, whatever you want to call it, these guys need to know what size they want to request from these. So we actually ended up making like our own versions of general purpose allocator and bump allocator, and you know, they're not too crazy. We kind of settled on a little bit of a simple buddy allocator scheme. So the buddy allocator kind of just says we'll give an example for like this guy. He's going to say, well, I know that like the page size is 256 bytes, and I know that probably like my minimum allocation size is probably going to be like 8, right? So we're going to have like 8, 16, 32, 64, 128 chunks, right? And in each of these, we will just only allocate in these size blocks. So if somebody asks for 12 bytes, we'll allocate from the 16 byte block. If someone asks for 45 bytes, we'll allocate from the 64 byte block, which means that we're doing a little bit of over allocation, but it's not too bad. And so what happens is we ask for like a 256 byte page from the system, in our case, our tiny page allocator. And if somebody asks for a 16 byte block, we just kind of like split this. So we could like store half of this guy in the 128. Then we split that guy again, store half in 64, split that guy again, split half in 32. And then we have like two 16 byte blocks. One gets stored here, one gets sent out to the user. And, you know, our goal here is that since using the general purpose allocator means that you have to do like manual memory management, and it requires like this like tracking structure, we should be favoring the bump allocator most of the time. There are times where you have to use the general purpose one, but like typically we're going to be favoring the arena allocator. And so because we know that, we have a good feel that these like list sizes should stay pretty small. So we can have like a pretty stupid implementation of these things and have it be kind of okay. And so we have made like a pretty stupid system here. It also will like merge things back up, right? So if somebody frees the 16 byte block, it goes in here. He goes like, oh, we're siblings. And then like he goes like, oh, we're siblings. Oh, we're siblings. Oh, we're siblings. And then like frees it back up to the system. Bump allocator, super straightforward. Super straightforward. We just have like a block and we move the cursor up and that's it. But then when we hit the edge, we get like a new block. We forget about this one. We get a new one and we move the cursor up. Boom, 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 boom. And because the page allocator is like remembering which pieces of memory that we have allocated from the system, we don't have to track anything like that in our bump allocator, which makes it simpler than I think a typical arena allocator would be, which would have to have some sort of like tracking to remember which pages it had. But yeah, I don't know. I'm pretty happy with that. I just thought I'd share. Yeah, I think it's a big win. And so those of you who've been like kind of like passively following the allocator project, this is the end of it. I think I'm going to merge the code. We're done. And I hope that was informative in some way. I guess we will find out over time. Maybe I will discover more problems with this approach later. But for now, it's feeling pretty fucking good, man. All right, peace out.